roles in telecommunications. I'm excited to share our work today. Atlas towards real-time verification in large-scale networks with a native distributed architecture. This is Zhuang involved with Yuehan Zhang. I'll start by giving some backgrounds on network verification and explain why we undertook this work. Then I will discuss problems of current data plane verification tools in large-scale networks and the problem-solving intuition. After this, I will introduce Atlas, talk about its key features, and share the results of our experiments. Finally, I will wrap up with our conclusions and thoughts on future directions. So these networks are large and complex. They include devices from many different vendors. Network devices come in various types and interact through many protocols. This makes managing networks increasingly challenging. In such an environment, network outages are quite common. This can be caused by human misconfigurations, such as BGP neighbor setup error or SPF wide error, and switch software bugs, and fiber damage, and so on. So to check errors, network managers use their experience and tools like traceroute and ISMP ping. However, manual troubleshooting takes a lot of resources. Network operators need to step-by-step determine the root cause of the error. It requires a lot of time and it needs a significant labor resources. Plus, it's prone to human error. If anything is missed, it can lead to bigger problems and later on. So, we need a powerful tool to check network errors. As a result, network verification was developed. It's an automated tool designed to analyze networks and identify errors. Network verification is divided into control plane verification, which input is control plane configuration, and data plane verification, which input is data plane forwarding table, and runtime verification, which monitors execution. Data plane verification, we call DPV, is significant as it is closer to actual forwarding behavior and demonstrates a combined effect of all configurations across the whole network. This discussion will focus on data plane verification. Currently, data plane verification tools use a centralized architecture. They set up verification service on a single node or cluster. This service gathers data plane information, such as FIB, from across the network for analysis. This centralized architecture helps ensure that data flows correctly and efficiently throughout complex networks. However, modern networks are often very large, include data centers with thousands of nodes, wide array networks, and large enterprise networks. These vast infrastructures make managing and verifying network even more challenging. As the number of network nodes grows, a huge amount of real-time data is sent to a single server. The server's computational capacity often can't keep up with the demands of verifying data in large-scale networks. And this mismatch can lead to delays and inefficiencies, making it harder to ensure routine network operations. Addressing this challenge is crucial for handling the complexity and size of modern networks effectively. More importantly, for large-scale networks like Wang, utilizing a single-point server to collect real-time data plane updates from each network device is impractical. The latency issues caused by physical distances are challenging to overcome. So, to address the challenges of DPV in large-scale networks, distributed scaling becomes a natural solution. Based on the architecture of large-scale networks, it is natural to think of going for dividing and managing the network into different areas, just like network designers do when they creating large-scale networks. On one hand, distributed scaling helps solve computational bottlenecks by splitting tasks across multiple servers. The distributed architecture offloads DPV tasks to multiple distributed components. This utilizes the computing power of each component, reducing the computational pressure of a single-point server in large-scale networks, thereby improving real-time performance. On the other hand, the distributed architecture adapts better to large-scale networks by locally collecting data plane updates from network devices. This means data doesn't have to travel all the way to a central server, ensuring faster and more efficient updates. So Atlas was born. Atlas divides the network into several disjoint sets of switches, each referred to as a region. Switches directly connect to switches in other regions, and forward packets are referred to as backbone nodes. We deploy a local agent for each network device named switch adapter. Switch adapter can operate either as a process within the switch or as an external process running on an instance, such as virtual machine, assigned to the switch. Then, we assign a manager for each network region called region adapter. This manager oversees all switch adapters in the region and receives this topology information in the region from the network manager. And last, we deploy a global manager for the whole network we named a center adapter. It acts as a global manager overseeing all region adapters, receiving global topology information from the network manager. Overall, Atlas uses a hierarchical distributed architecture from the switch to the region and to the whole network. So, with this architecture, how to efficiently utilize it? Traditional DPV tools require 2 steps to complete the verification task. The first step is to build a model, which can express the forwarding behavior of any packet in the network. And the second is to get verification results based on the model using a verification algorithm. Therefore, to be able to adapt to distributed architecture, Atlas offloads these 2 steps. First, we distributed modeling. Atlas distributed the model into 3 layers. The first layer, we distributed the model to each switch. Specifically, based on the routing tables of the switches to which it belongs, the switch adapter locally maintains a model we call switch model. The model represents the packet forwarding behavior within the switch. And the second layer, we distributed the model to each region. Each region adapter combines the switch models to generate the region model. The region model can represent the packet forwarding behavior within the region. And as the last layer, we build a model for the whole network. The region adapter compresses the region model and passes it to the center adapter, and the center adapter generates the backbone model. The backbone model can express the forwarding path in the whole network. Then, Atlas distributed verifying. Atlas designed different offloading methods for different DPV tasks. For example, for the loop task, that is, we want to know if there are packets in the network entering the loop. We divide all the loops into intra-region loops and inter-region loops. For intra-region loops, we check them through region models. And for inter-region loops, we can exact their critical paths, that only the paths of backbone nodes are included. And we complete the verification through the backbone model. Other tasks, Atlas can similarly split and distribute the verification to achieve high parallelism. This is an example of Atlas workflow. We first maintain a hierarchical model, just like what we just talked about, and each layer is maintained in parallel. Then we offload the verification task and distribute it to the distributed components. Just in this example, the verification task is a user-defined policy which requires packets with destination IP forward from A to I and passing through switch E. We split the task and assign to corresponding region adapters. Finally, the distributed components complete the verification task and give the results. Now we introduce the evaluation part. We implemented the Atlas and compared it to the state-of-the-art approach using simulated datasets and the real deployment. Initially, we conduct simulation experiments on a testbed using 10 synthetic datasets widely recognized by the community. The first 7 are wine datasets synthesized from popular topologies, while the remaining 3 are data center datasets. FT48 is a switch-based data center topology, and Fabric 4 is a cloud-based topology. We utilize BGP as a sole routing protocol and Batfish as a network simulator to run and collect their forwarding states. To further stress test Atlas, we synthesized a large-scale enterprise data center network named B4DC. And this involves synthesizing several FAT20 DC networks, each with a unique IP address space, and connecting them using B4 2018 as a backbone. We simulate a burst update scenario where a large number of data plane updates occur within a short time frame, such as during a greenfield deployment or network disruption or network recovery. Experimental results shows that compared to state-of-the-art data plane verification schemes, Atlas is over 10 times faster than the fastest centralized DPV tools and 7 times faster than the leading distributed DPV tools. We also simulated a continuous update scenario by randomly generating 10,000 new rules and sequentially inserting them into the corresponding switches following the burst update. Atlas still maintains a significant advantage in performance. Across all datasets, Atlas verifies at least 96% of rules updates in under 10 microseconds, whereas the lower bound for other tools is less than 1%. Additionally, the 80% quantile verification time for Atlas is up to 7 times faster than the fastest centralized DPV tool and 2 times faster than the distributed DPV tool. We evaluate the performance of Atlas by deploying it onto a commercial data center network with 500 switches. The network uses a factory architecture, which we partition into 10 regions. We completed the DPV task and statistics on the verification time in the burst update scenario. All DPV tools did not detect any errors. Then we simulated loop faults by root aggregation, and all of the DPV tools detect the inject faults. We compare the verification time with the fastest centralized DPV tool and the distributed DPV tool. The result shows that Atlas still get real-time verification in real deployments. So in summary, we present Atlas, a native distributed real-time data plane verification solution for large-scale networks. To achieve this, first, Atlas designed a hierarchical distributed architecture for DPV in large-scale environments. And it employs a native approach to maximize architectural parallelism. Both dataset-driven simulation and real-world deployment shows that Atlas offers fast and scalable distributed verification. In the future, we plan to explore more efficient data structure for transport between distributed components. Additionally, we aim to enhance support for fault-tolerant scenarios. Okay, so that's all about it for now, and thank you for your attention.